Hi, I'm Anqi Luo.
I'm Ting Luo.
I'm Zheng Yichen. Our third project is high-order Markov chain models for dynamic prediction of sleep quality. Our project is supervised by Professor Rolf Norman. Suppose one day you are forced to wake up by your alarm clock, but still feel tired and sleepy. You may wonder why you are still not energetic when you have spent enough time sleeping. It is because that you are forced to wake up in your deep sleep period when your body is recovering and all your body functions are in static mode. This kind of situation happens a lot in daily life and largely influences our working and studying efficiency. Nowadays, there are some sleep tracking applications on phone that can record users' sleep quality curve of the whole night, which is shown on the screen. These applications also have a smart alarm clock function, which can wake users up once it detects the user is not in deep sleep. Inspired by this function, we wonder if we can find a model that can help solve the question, how to wake users up at their lighted sleep based on their personal historical data in a given time interval.
Normally, if we know a series of observations in order and want to predict the next one, we would like to fit these observations into a certain model. The model we choose to use is Markov chain. The Markov chain is a probabilistic model used to represent dependency between successive observations over random time. In our case, we consider a discrete time random variable xt taking values in the finite set 1, 2, 3, 2, n, where the values denote different sleep quality state. Our goal is to predict or explain the value taken by xt as a function of the values taken by previous observations of the same variable. The first-order Markov hypothesis says that the present observation at time t is conditionally independent of those up to and including t minus 2, given the immediate past time t minus 1. The only factor that will influence its next sleep quality state is its current sleep quality state. Let's first categorize users' sleep quality into 3 states. The graphs here describe a simple first-order Markov chain. The probability of staying in the same state sleep quality is pi11, and the probability of moving from light sleep to moderate sleep is pi12. And it's possible that it will move directly to deep sleep, which is pi13. Here is the transition probability matrix for this model. The main feature of a stochastic matrix of Markov chain is that the summation of each row equals to 1. One question is how to estimate these parameters. We need to introduce principle of maximum likelihood estimation to help solve this question. Maximum likelihood estimation is a method of estimating parameters of a statistical model when observations are given. Likelihood describes the plausibility of a model parameter value given specific observed data. If the events are independent and we know the probability of xi is pxi knowing the distribution is theta, the likelihood of observing all the events is to multiply all the probability of corresponding event. The goal of maximum likelihood is to find the optimal way to fit a distribution to the data. There are a lot of types of distributions for different types of data. By fitting data into a distribution, we can simulate a new series and make predictions in terms of it. Let's take stage 2 moderate sleep as an example. If we sample 1,000 times starting with moderate sleep state and we record the next state the users will enter. Suppose that there are 100 times that the user will go from stage 2 to stage 1, 700 times that the users will stay in the same state, and 200 times the users will enter stage 3. How can we get these parameters pi given these 1,000 samples? We want to find theta that maximize the likelihood of all the events happening, that is pi21, pi22, and pi23 in our case. Holding other parameters fixed and changing only 1 pi each time, we will find different values of pi ij corresponds with different likelihood of observing the data. We want the location that maximizes the likelihood, and it is the maximum likelihood estimate for the parameters. We can use the same way to estimate the maximum likelihood estimates for other parameters as well. For the convenience of computation, we usually take log of the likelihood function and transfer it to summation of logs. If theta contains n unknown parameters, we need to take partial derivatives of all the parameters and get n equations. The solution to this equation set is the extreme point of the log likelihood function. Go back to our example. The likelihood we want to maximize is pi to 1 to power of 100 times pi to 2 to power of 700 times pi to 3 to power of 200. Then we take logarithm of it and take the partial derivative of the parameters. We can find that for the first order Markov chain, the best parameters of transferring from one state to another is given by the jump frequency. In some situations, the present depends not only on the first leg, but on the last n observations. This is high-order Markov chain. If we consider two legs, which mean we taking the previous two states into consideration, we will get the second-order Markov chain. The reduced form of the matrix corresponding to order equals to 2 and state equals to 3 is displayed as below.
Once we have chosen our model, we can process our data accordingly. We export our personal sleep quality curves for 65 days from our sleep trackers, with one curve corresponding to one night, and we write a curve extractor to read only the curves. Given the graphs of curves, the total sleep time of each night, and the size of the graphs, we compute the number of pixels corresponds to 5 minutes and extract the point in form of states 1 to 5 every 5 minutes, which gives the transformed curve. While the highest point of the original sleep quality curves represents the lightest sleep, our transformed curves perform the opposite, that the lowest state 1 stands for awake. We store the states in the matrix, where the ith row stores the data of a night, and the jth column stores the data at j times 5 minutes of the night. We can gain the transition matrix of MC2 model by computing frequencies as we said before. We did the dependency test to check whether the parameters we computed have the Markov chain property or not, and luckily it passed. With this transition matrix, as long as we know two successive states, we can check the transition probabilities to each state at that next point. In this way, we can simulate a sleep quality curve for the whole night by randomly selecting the next state repeatedly, but only select in accordance to the corresponding probability of each state. An example of the simulated curve is shown on the right.
As the number of states and the order of Markov chain increase, the number of parameters of Markov chain becomes extremely large and prevents its estimation. So we try to use other models to fit our data. The mixed-to-transition distribution model gives different weights to transition probabilities at different steps away. In our model, we give different weights to transition probabilities a step away and 2 steps away, and the transition matrix pi in our model is different from the transition matrix in Markov chain. The matrix pi here is a 5 by 5 matrix gained by numerically maximizing the log likelihood, not by calculating frequencies of each transitions. The MTDG model is a further development of MTD model. It not only gives different weights to different steps, but also assigns different transition matrices pi to different legs. So in our model, we have 2 separate matrices to store transition probabilities at 1 step away and probabilities 2 steps away. The matrices and the weights in MTDG model is solved by iteratively maximizing the log likelihood of the model. However, the method of calculating the transition matrices are too complicated, so we excluded it from this video. After build the MTD and MTDG model, we can generate the sleep quality curve for the whole night using the same method as MC model, and the curves are shown respectively on the screen. After building these models, we compare the goodness of fits of different models by using the Bayesian information criterion. The Bayesian information criterion is defined as -2 times the log likelihood of the model plus p times log n, where p is the number of independent parameters and n is the number of data. The big criterion not only penalizes models with their log likelihood, but also takes the number of parameters into consideration. The lower the big a model achieves, the more pertinent it is. From the table with the log likelihood and the peak of the models, we can see even though the third-order Markov chain achieves the smallest absolute value of log likelihood, the second-order Markov chain has the lowest peak value. It is because the number of parameters in the third-order Markov chain is too large, so the peak value increases a lot. Hence, in the following prediction procedure, we will use the second-order Markov chain model since it has the best goodness of fits.
So far, we have finished discussing about different models. Let's get back to our main question. That is, given a time interval, how do we wake users up at their light sleep? We use MC2 model to do the prediction in the 30-minute time window. Based on the MC2 model, we set the observation time interval to 5 minutes, which gives 7 observation points in total in the 30-minute time window. At each observation point, the algorithm will calculate the cumulative probability that a lower state will appear in the remaining time window. If the probability is less than a certain threshold R, the algorithm will decide that it is the right time to wake up and then terminate. Otherwise, it will wait until the next observation point. If the algorithm does not terminate in the given time interval, it will decide that the user should wake up at the end of the 30-minute time interval. Here's a more concrete example. Suppose the time window is 7 a.m. to 7:30 a.m. Then at 7 o'clock, the algorithm will compute the probability that a state lower than the current state 3 will appear in the remaining 30 minutes. When it finds that the probability is lower than R, it waits until 7:05 and checks the probability at that time, and so on. We test our model on randomly selected intervals on our dataset, and this is one of the tests. We can see on the left that the prediction result is the last observation point, and it differs from the actual minimum point. And on the right, after the prediction result is projected onto the original sleep quality curve, it is actually quite accurate. But the opposite situation may also happen. To find the optimal threshold R that gives the optimal result, we try to minimize the error rate of the prediction result, which is the percentage of difference between prediction result and the actual minimum point. We find that the error rate is stable when R varies from 0.1 to 0.2, so we arbitrarily set R to 0.15.
There are two methods that can be used to build a traditional alarm clock. The first one is to directly wake people up at a certain time, for example, 7 a.m. No matter which sleeping state you are in at 7 a.m., you will be waken up. The second one is the method mentioned at the beginning. In a given time interval, for example, between 7 a.m. and 7:30 a.m., you will be wake up once you are not in deep sleep. We compared our model with these two traditional methods, and the error rate of each method is shown in the table. We can see that the error rate of our model is the smallest, which suggests that our model can find the latest sleep moment in a time interval more accurately and help people feel better after waking up. For our future improvement, we have three main directions. The first one is to try different models to fit our data, for example, continuous time Markov chain. Secondly, for now, to wake up at 2 a.m. or 8 a.m. is not distinctive, and we use the same transition matrices to calculate them all. But the more you sleep, the probability of waking up is actually increasing, so we'll try to solve this problem. Thirdly, we will build a new balance between sleep longer and sleep better. We will try to build two different models and allow users to choose whether they want to sleep longer or not. We will also try to apply this model to different fields, for example, stock indices prediction.
Finally, we want to thank our project mentor, Professor Raoul Norman, who inspires us a lot and has spent much time discussing papers, mathematical methods, and our project with us. We really appreciate his patience, and it is impossible for us to complete this project without his help. Thank you.